quite a couple of papers that have been doing some more work outside of just plant demography. And of course, we have some honorable guests here who can relate to that. But as far as selection is concerned, our lab did something which was already looking into selection in South Asia, but in a very different framework than what I'm going to present now. And selection also because why South Asia is given this big different environment that is around here. This leads to actually a lot of different selective pressure. So it's a very fertile ground for selection to happen. And maybe more I would say, pertinent to when you have to look at nowadays population. Also, the structure of population is really interesting fact that can be exploited for further analysis of different methods. But so selection. I'm speaking about Ohana. So if I'm speaking about Ohana, the software which I use for that, I need to make a detour first by structure. And what do I mean? I mean, we have a lot of because the paper that is doing that is when you say that it's actually based on the framework on the previous paper, as I mentioned, which is a facet mixture analysis and population tree estimation. And by structure method, I guess by now you are all familiar with it, but I'm not going to be deterred by that, and I'm still going to stick to what I have to say because I made the slide, so I might as well go with it. And as is quote the paper, it's just structure method is actually a cluster algorithm that helps you classify individual in a sample fractionally into discrete sensitive component, which is kind of a mouthful, but now you're pretty familiar with all these pictures. And so just to briefly go over it, this is the population as it was simulated, and this is the population structure as it been reconstructed with Ohana. And usually we number the number of this ancestral population, or what we call ancestral component, by a K number. And K is not necessarily for cluster, but it's just like the usual constant in mathematics. So we usually use like some incremental things. And little disclaimer in that, I think that probably Thomas also mentioned, is that it's very arbitrary this K that you use, and so bear in mind with that it's not necessarily a fully biological background behind it. So that's really one of the first caveats that we have to bear in mind. So as my abstract said, this is just like a proof of concept. So we used just the samples from the 1,000 genomes, and so we used, because as we see further down the slide, there was a reason why I used the British and not other population, but here they are. So what do we get for structure? So this is what I got for when I was exploring the structure analysis, going from increments of K4 to K8. And what I'm going to focus on is, because as I said, it's very raw results. The only thing that I really sort of thought was pertinent in this idea, because what Ohana does is that it's going to look at try to detect the selection signal in ancestry components. So it's going to try to see what is actually selected maybe in the light green or in the dark green or in this whatever kind of component. And so I didn't necessarily want to go yet in higher case, where maybe if you look at this component or this component, there might be something interesting, but so far I didn't have really time to maybe justify why and what be behind this component. And so when we look at K5, one of the what structure does as well is for Ohana is that you can get a tree out of it, which is always nice to get. One thing that you have to keep in mind is that the tree structure itself is probably pretty reliable. The actual distance are prone to maybe under or overestimation. So this is for K5, and so we have this light and dark green. So what I would call my South Asian components are here. And when we jump to K6, then this dark green component, which was the light green. Oops, going further. Start to already get this is the Telugu samples, which so they tend to a portion of these samples have to get their own components, which is still found in minute traces in some other populations. But as I said, very first insight. I'm not going to dwell onto it, what could be the reason behind it, but you know, it is what it is. So the selection, the Ohana does that by you get your genome-wide virus matrix, and then you just use that and try to find in each of these components what kind of descending frequency deviate from your average. And in the paper, and this is why you see why you use the GDR and not the CEU. In the paper, they used this frog population, and so as a proof of concept, at least more for me than you know for anything, what I did first was to see whether my own results at the K5 was actually recapturing the same signals. And now starts the period where you're going to get a lot of these slides. And the first ones, you're going to have, I will have something to say, like we do indeed recapture like some famous poster child signal selection in the Europeans, like SFC 45A2 with famous clips here. I also managed to get the SFC 24A. Interestingly enough, like this is the lead thing, but I still got something there around it. But again, didn't have time to look further on it. And then also, because it's just one on the arc and the ORC2. Because it was also there in my data, or at least in the sample set that I used, I also looked at so in the Chinese. And one of them is the first cluster, and the same we recapture the lead snips there, and we'll get back to stats in a little bit later on. So just sort of bear in mind of what they look like here. And also the normal ADH1B and the ADAR gene, right, which is responsible for teeth and hair. But say, okay, nice and dandy, so you replicated what has been already shown before. What do you have to show? Well, if I look at K5, and I'm just going to focus first on the darkening component, and now it's going to be even more, sorry for the word, it's not very the most appropriate, but very sketchy. Because I didn't have, again, time to focus and try to see more carefully what it is. But nonetheless, we do, I do find something else. So, for instance, I have a lead somewhere in this AMPH gene, which is, but it's, not antigen, the Stickman syndrome that with breast cancer. I don't know if that's relevant or not yet. I don't know exactly. But even though, as you may know, it's not the perfect fit in the cluster, but on the other hand, it's nearby. So we have some genes which are involved in the adaptive immune response and the innate immune response. So maybe it could be something, just some cis-acting things or relevant. I will need to see more about it. Another, and this is just the top signals. I mean, there are many more. Which is next to 4, which is linked with neural development, and things like this. Also, one of the family ones that has been shown in Asian is POO3. POO3 has been found also. There are some also Jiwa seeds. Here, like I think this one is linked with neurotism, and one with blood metabolism. And then you have this for well known in South Asian is the Basques cluster, because they have it has been already shown the selection on the South Asians because of the dietary that they have. But here you can see, if you sort of like recall the slides that I had before for East Asian, here I don't even have like this. And there is a good reason why you don't recapture this known indeed for the Basque cluster in South Asian. It's because the actual adaptive thing is a deletion. It's actually also an insertion. And the data that I use is actually only SNPs, which are above the substance ratio. So this type of captures. But it would be nice to see if Intel actually could be also worked and capture this framework. And then there are some other things like, right there. I mean, like, okay. Here, at least, what I was using is similar twist. I didn't have anything, but this can be due also to the window that you use, because then Parash would maybe know a bit more about it. But there is some long intergenic non-protein coding, which is just a little bit, right of it. In the paper, the actual original Ohana paper for selection, there are a couple of things also that they discuss, which is also belonging to this class of longitudinal different protein coding genes. But what does it do? No, I don't know. But now if we look more at this more widespread light-ring complex, again, couple of hits. These are the topics. There are the GWAS hits with white matter structure, and then some other with phase or neurotism. So it's kind of this grainy things around here. Another one, this one, again, I don't really. It's more of a listing of the things that I found. I can't give you any real explanation as to what could be the biology of the reason behind it, but at least at least I have something to work with. And then there are some things like that where I didn't even try to really look into it. I mean, as you can see, there is a slew of things. It's going to take really time to try to freeze out and see what could be there. And that's a bit difficult, especially because I think this software that I'm using is kind of connected also with some of the database, but maybe the representation of sausage and samples is there is not so well done. So difficult to really see. Again, for pads, whether in the light green or in dark green, I don't see it, but for some reason, because this is an insertion, so there was no chance for me to find it. But then if you allow me to finish on a very completely speculative and super wild thing, which I should not take any fatality for, I will still go for it. So there was this small hit there. Okay, maybe this thing is not super relevant, but what I really found very interesting was that nearby there was this Adam30, and that's actually Adam is metal protein chemistry, and it's related to actually the snake phenotypic. So has there been any pressure from snakes around here? I guess you probably should know more than I do, but yeah, the region is pretty known for having snakes. So are we on the way to get some super Indian with resistance to venom? But yeah. So as I said, try to keep it very brief. And so what could be the conclusion and the further direction? Well, I think as far as the proof of concept, of course, authors, when they present their methods, they have like some good reason to say that that works. But at least for me, you never know. Sometimes it might be different. But when I managed to replicate at least the results that they had in the paper, I was fairly confident that the correlative stuff. And so there are several specific ancestry component specific signals that are related. But again, very preliminary, needs further inspection. And of course, there are different ways. As this is relying, the very first step of the method, rely on the structure graph. It's going to be very sensitive to the choice of population that you use. It's going to be very sensitive to the population, to the K number that you choose. So this is all the kind of things that can be tweaked out and sort of really have more refined, I would say, ancestry components of South Asia. Of course, I'm really interested in selection. You need to use a different variety of methods because all of them rely on different frameworks, and they will catch up signals which are either later, or younger, and so you need to really cover everything. I don't remember one of the presenters really presented that, and his name was very difficult for me to say. But on the other hand, I know that this work is actually done a bit in collaboration with Ajay, but he's going to really present some things there. And then, of course, just sampling. We are limited with what is available, what's out there, and for some of the creators, it would be interesting to have more dedicated and very focused sampling of South Asia. There are many questions that I'm very interested in, but I don't have the samples for that. And I have some things in mind, but I don't necessarily want to sort of get out of it with it because that really requires some very social things. But anyways. So even though so far this work has been done only by myself, I still have to single out the things that you know that it's not the right way. But I think the Ajay, not this one, this Ajay. was the one who, sort of like helped me and give me a bit some advices into these things. So with that, I would say, Daniela, thank you. Merci.
Thank you, Doctor. Now we are open for questions. We do have time. You stick up to your time very well.
Yes.
So, are there any questions from the audience, please?
But don't feel obliged. We can skip ahead, and so we can, keep more time for the ones later on.
I'm looking at the SNPs or mutations.
Yes.
Or causing disease, associated with disease. Is there a possibility to go back to an individual?
You want to go back to the slides?
An individual, that's right.
Sorry. Yeah, sorry.
You took samples from individuals.
Yeah.
That man is having some susceptible gene mutation.
Yes.
For a disease.
Yeah, but this is just a sudden genome thing, so
Okay, wherever but I didn't think with that.
Yeah.
The individual. Ultimately, when you're looking at the diversity and precision medicine, some sort of this sort of approaching the families and advising them for the true clinicians.
Yes.
This should be a part of this study. Otherwise, you have got so many genes, mutations.
No,
These are very serious diseases.
Yeah, I know. I do agree. In a way, I think this what I present is a bit similar sometimes to what GWAS can be done. That you have just topics, but you don't necessarily have the biology behind it. I mean, I'm not trying to speak on GWAS studies, but I just say that there are sometimes we stop a little bit at we just we get a hit there when it's really behind that we don't necessarily know, but. Yeah, it definitely requires a bit more careful things.
You will validate it. Going back to that.
Yeah, I agree. Yeah, Ashish.
Yeah.
So, Ohana is supposed to be ancestry specific, right?
Absolutely.
Right. Okay. So, and my understanding is that you're looking at the Eurasian component?
Kind of. Because that's my grip with the thing, actually. I present some things where I'm still sort of like in between. Because, if you go back to, we're going to get there eventually. Again, what the selection looks, it's going to be in your states which are deviate from the genome-wide, which is calculated from the entire things, and what FMPs in this component deviate there. So why should I believe more the hits of, or should I mean, some of the hits would I again K5, would I still recapture them in some K6 or in K7? Because, for example, this light tree starts to break into two, so I didn't have time, but I actually, it's running on the cluster, and I really would like to see, for instance, when this company splits in two, or like in other things, what is the overlap in between the things? How much SNPs can you really get into one such like very high specific component? Because as you know, with structure analysis, you're trying to maximize some of these things, so you may induce some, I don't know, undue bias in there, but I don't know, because in some ways, you still capture some of the most famous signal in these components. So yeah, I don't know. I'd like to see, but yeah. So that in that sense, in a way, in a perfect world, we could have a transect through time, and again, we're going to hear, we get mtDNA, but I know South Asia is going to be a real challenge to get that. But the best world would be to get some posts all around through, the time transect, and you can look at your, use your favorite things in your favorite genome, things like that, rather than through, it's a proxy which has been, created from statistical inferences. But yeah, nonetheless, it is what it is, and it might still be something interesting to get there.
Okay, so as a follow-up, did you look at lactase?
No, good question. Yeah, completely forgot. I mean, some of this, I know, yeah. I mean, some of, for example, ADA was not in the paper, and it's ADH, and I was just like remembering some of the famous ones, but somehow, the blind spot, the elephant in the room, I didn't get it. Yeah,
Mate's going to be really mad at you now.
I mean, I have it there, probably can look at it, but yeah, thanks for putting it. maybe you're taking your job.
Looks like nobody has a question, but maybe I do. So these are some of the tools and techniques that we are trying to get the best possibility of analytical tools when you use your GWAS, the GWAS, right? And trying to identify those. So when you use the word selection, does it mean, in your case, are you pointing to natural selection, or is the selection of samples?
No. This is really natural selection of objects. It works on the assumption that if you have a deviation of your SNP compared to your global frequency, that if you have deviation, one of the likely explanations, it could be due to natural selection, and that's the only thing that we pick up. After that, the downstream of the explanation of why this notice has been picked up, why is it in such a high frequency, that's when we need to be a bit more detective work.
Yes, it's the interpretation, right? Yes, to get it correct.
It's the same. As I said, my venom explanation can be totally right and then more likely to be totally wrong. But
yes.
I think it's cool.
All right. Thank you so much. Thank you, Dr. Pennarun. Now we move on to the next.
No, we don't move.
Thank you so much for remarkably presenting the exploratory view of the South Asians and specific selection with the prime focus on Ohana. Now I would like to call Ma'am Vanderida to facilitate our speaker, Pennarun sir, with the moment.